Today we're going to cover relationships and functions, basically an introduction to functions. So what is a function? A function relates with an input and an output. Think of a machine. If you put one thing in, you're supposed to get one thing out, and somehow they need to be related. The easiest, most clear example of this is a vending machine. You put in $1, you get out one food item. If you put in $1 and you get out two things, well, that's great for you, but not for the owner of the machine. If you're the owner of the machine, it's a broken function. And the opposite is true also. If you put in $1 and don't get anything out, then it is a broken function. You have to put one thing in and get one thing out. So if I'm looking at the numbers, I have a function here. One number in comes one number out, etc., etc. Here's an example of not a function. The 7 goes in and two numbers comes out. That's like putting in your $1 and getting out a bag of chips and a bag of M&Ms. It's a broken function, and if you're the owner of that machine, you're going to go out of business really soon. You cannot have a function where you put one number in and get two different things out. You can, however, put two numbers in and get the same thing out. For example, you have students riding a bus. If you have 68 students, you only need two buses. If you have 75 students, you still only need two buses. But if you have 125 students, then you need three. So I put one number in, I got one number out. That doesn't break the rules of the function. For example, with your vending machine, if you put in $1 and you want a bag of Fritos, then that's perfectly fine. It's a function. But if the next person puts in $1 and also wants a bag of Fritos, that function's not broken. You just want the same thing. And that's what's going on here. You have 68 students can fit into two buses. 75 students can fit into two buses. So you're not breaking the function. What breaks the function is if you put in a 7 and you get out a -1 and a 0. Two outputs. Now a function can look two different ways. We're used to writing equations y equals 2x, and that should look similar to slope-intercept form, y equals mx plus b. We can write the same equation as a function. F of x is equal to 2y. So we've talked before about how the y and an f of x are basically the same thing. Now we'll talk about the output and the input. The output is your f of x, or the y value. The solution. Your output is dependent. What is it dependent on? It's dependent on the input. So if I put a 10 for x, it's going to change my answer. If I put in a 5 for x, it's going to change my answer. So the output is the y value, and we remember that the y values are also called your range. So the output is dependent. We can call it the y value, and it's also going to be your range. The input is independent. That's the number that you're starting with. It's going to be your input, and it's also your domain because it's the x value. So input, x value, independent, domain. Now you can create a table for these, and sometimes you see an input-output table. So here the input, the number we're putting in, is always our x value, and your output is going to be your range. So if I have x times 2, 0 times 2 is 0. My input and output happen to be the same thing. If I have 1 times 2, then I get 2. If the x value is 7, 7 times 2 is 14, etc. Now these are your key points here. Your domain, you should already know, are the x values. Now we know them as the input or the independent. So x, input, domain, independent. Meanwhile, the range are your y values. You should have already known that, which are the output, and they are dependent upon whatever you put in. So if I put in an x value, I get out a y value. That's your output, and that's why it's dependent, and it's also called your range. Now, the vertical line test. The vertical line test is an easy way to see if a graph is a function. Basically, you draw vertical lines. Remember, vertical lines go straight up and down. When drawing the vertical line, you should only hit your graph once. If you hit your graph more than once, it's not a function. Now here's the example. They have a sine wave and they drew the dashed vertical lines to test it. So they drew 2 just to be safe. At no point when I draw a vertical line will I hit the graph twice. So we know it's a function. However, over here we have an absolute value of y function. The vertical line is going to hit my graph twice. Because I hit the graph twice, what that means is I have 2 outputs. Remember, the input is the x value. So my x value is right here, and I have 2 outputs. If I have 2 outputs, it's not a function. Now, let's do some more examples. The first example depends where you draw your line. If I draw my vertical line over here, I'm only hitting it once still, but eventually I get to where it's crossed over. Now, where it's crossed over, I hit it twice, so we would say not a function. A parabola. Now, those should look familiar. In fact, all the rest of these graphs are graphs that you need to know. The parabola, again, if I go up and down and draw my vertical lines, at no point will I hit it twice. So that is a function. A circle. Well, if I come out at the edge and just barely clip the end, you should know that as a tangent line, then it might look like a function. But just like the first example, I'm going to hit it twice at everywhere else on the graph. So that would not be a function. Hyperbolas, obviously not a function. I'm going to hit the line twice. I have 2 outputs, so you would say no. And the y equals 1 over x, no matter where I put my vertical lines, I'll only hit the graph once. So the answer there is yes, it is a function. Evaluating functions. This sounds complicated, but it's not. It simply means to substitute, something you already know how to do, and then solve the equation. Now, it can be written in equation form or in function notation. We'll do a couple examples. Y equals 3x plus 2. Find y when x equals 7 and x equals -4. Simply substitute. Whenever you're substituting, you always use parentheses. So you get y equals 23 when we substitute or evaluate for 7. If I'm going to evaluate with -4, I get, and y is equal to -10. Now, when we evaluate these, sometimes they'll want the answer just like this. Well, what is your output? My output was 23, and my output is -10. But oftentimes, they'll want it in point notation. So that means you'll put both your input. I inputted a 7, and I got out a 23. I inputted a -4, and I got out a -10. All right, now this one's written in function notation, so let's go ahead and run through it. F of x equals 1.5x minus 5. Find f of x when x equals 6. Now, because x is equal to 6, when we write function notation, and this is one of the advantages, we'll say f of, instead of writing x, we go ahead and start substituting, f of 6. This makes it very obvious and clear what my input is. That gives me 1.5 times 6 minus 5. So wherever I have an x, I simply substitute it. Now this makes a lot more sense when you're thinking about reading the problem. F of 6 is equal to 4. I have an input and an output. It's much more clear than saying y equals. So I know what both my input and output are. Or you can write it in point notation where you'd say 6, 4. And then we'll do the next one. My input on this one is -2, and my output is -8. Now don't forget that domain and range. If they asked, on this one your domain would be -2, and your range would be -8. In the first problem, your domain would be 6, and your range would be 4. Now sometimes they're just going to give you a pretty picture and make your life easy. This asks us to evaluate the functions at 0, 1.5, and -4. All you have to do is read the graph. So for each function, evaluate f of 0. So f of 0 for this would be at 3. So we could say f of 0 will equal 3. Then f of 1.5, well, here's 1, there's 2, so 1.5 is directly in the middle. That puts us at 4. So f of 1.5 is equal to 4. And the last one, f of -4. 4. So I come all the way back to negative 4 and I look at where I'm at. We would say the function at negative 4 is equal to, and my y value is 4. So the f of 1.5 and f of negative 4 come out to be 4 at the same exact spot. That's perfectly fine. We can see that this would pass a vertical line test, so yes, it's a function. And I hope that makes it obvious that the input is the x, so we put in a negative 4 and we got out a positive 4. We put in a 0 and we got out a positive 3. Input is the x and the output is the y. Now this problem wants us to create our own function and then solve it. It says the tickets to a concert are available online for $35 each plus a handling fee of $2.50. This is where all the key information is. $35 each. That means if you have one, you spent $35. If you have two, you spent $70, etc. So $35 for each one you have. Why do I keep saying that? Because that is where our variable is. 35 times each one. How many do we have? Well, we don't know yet, so we put the variable. Next is pretty obvious, a plus sign, and then plus how much? $2.50, 2.5. So this is our function. We'll use C instead of F. Why? Because C is cost, and we'll use a T. So instead of putting an X there, I'll put T for the number of tickets. So we have the cost of tickets, C of T, is equal to 35 each ticket plus $2.50. Now we just evaluate for the number of tickets. They want 4 tickets. We just plug it in. Remember to always use parentheses when you substitute. That gives us C of 4 is equal to 35 times 4 plus 2. Well, 35 times 4 is 140 plus the 2.5. That gives me 142.5. But remember it was in dollars. So put the extra 0 there to make it a dollar and the dollar symbol. So you would say the cost of 4 tickets is $142.50. Alright, here's one more word problem. Recycled CDs Incorporated offers a choice of 5 used CDs for $27, with each additional CD costing $3. Write a cost function for purchasing 5 more CDs. What will the cost of buying 11 CDs be? Let X represent the number of CDs over 5. So this one's written a little bit different. But just like in the last problem where we had $2.50 that was going to be automatically added, here the 27 is automatically there. You have to start with 27. So we have $27 plus however many more CDs you get. Well, how much are each additional CD? Each, that means we're going to be multiplying. Additional CD is $3. So we have $3 each with the 3x. Now typically we'll write the x in front, so I'm just going to rewrite that. And now we have cost again. So it's cost of x is equal to 3x plus 27. We didn't use C because CDs and cost. X is just a much better thing. Plus, they told us to use X. Make sure you're reading the directions. So now they want to know what the cost of buying 11 CDs will be. Now this is where people tend to make mistakes. They throw an 11 in there. Just like in the last problem, we put a 4 for tickets. But that's wrong. How many CDs do you get for $27? This $27 is going to give you 5 CDs. So how many more CDs do I need? Well, the simple math would say 11 minus 5 leaves us with 6 CDs. So we're going to say C of 6 is equal to $45. Now, why did I put in 6? Because I only needed 6 additional. It's $3 per additional CD. I need 11 total. So the 6 additional CDs is $18 plus the original 5 CDs was $27. And that's where I get a total of 11 CDs for $45. So the answer to your question would be 11 CDs cost $45.